Let's work out a simple example. We have been given a square loop, a square which we call ABCD, and carries a current I, which is a length L, and our goal is to calculate the magnetic field at this point. Let's solve this. The solution will involve using the same equation that I derived last time. That is, if you have a wire which carries current I, and you want to know what the magnetic field at any point P is, then that magnetic field in magnitude turns out to be mu naught by 4 pi I divided by A times sine alpha plus sine beta. And alpha and beta are the points from that, no, they're not points, they are the angles. The angles obtained by these two extreme rays with respect to the center. Okay, so if here is alpha and here is beta. It's very tiny, I hope you can see it. Okay, so I'm pretty sure you can sort of see where we're going with this. So what we have to do now is apply the same formula to all the four sides of the square. Okay, let's quickly do it. So we know what this distance is. This is what we are interested in. That distance is L by 2. That is our A. That's the perpendicular distance of this point from this wire. I'm calculating the magnetic field at this point due to that wire AB. So I'm just going to calculate due to AB. So due to AB, the magnetic field at point P is going to be mu naught into I into 4 pi multiplied by length, that is L divided by 2, the perpendicular distance, times sine alpha. So this is the alpha and this is beta. Actually, anyone can be alpha and beta, it doesn't matter. But look, it's a square, it's 45 degrees. I hope you can see that. The whole angle is 90, that's 45. So you get sine 45, which is 1 over root 2, plus another sine 45, another 1 over root 2. That gives us something annoying going on in the background there. I'm extremely sorry for that, but we have to continue. So that gives us 2 pi L times 2 divided by root 2. And this 2 cancels, so we get mu naught into I divided by root 2 pi L. That's the magnetic field due to one particular wire, and let's figure out the direction of that. Now the direction can be figured out in multiple ways. Either you can go for dl cross r. You can think of the dl vector is this way and r vector is this way. So if you do a dl cross r and you use your right hand rule, you're going to see that the magnetic field is in to the plane, into the screen. And so this magnetic field over here is going to be into the screen. That's into the screen. Now notice something, that the magnetic field due to BC is going to be exactly the same, because if I draw a line from here to here, that is also going to be L by 2, and these angles are also 45 degrees. And the same will work for CD and also for AD. That means the magnetic field due to all the others are exactly the same. So all I have to do now is figure out the direction and either add them or subtract them. So let's do that very quickly. Here dl vector is this direction and r vector is again downwards. You do a dl cross r, thank God the background thing stopped. Alright, so if you do a dl cross r, again notice that the magnetic field is going to be inwards. Awesome. It's going to add up to this one. What about the magnetic field due to CD? Well, same exercise. dl is this way, r is this way, dl cross r inwards. Excellent, adds up. And I'm not going to check that over here. You do that last check, convince yourself that that's also going to be inwards, and hence this problem is solved. The total magnetic field at point P, total field, this was due to AB itself, AB only. Total field is now going to be just 4 times that value. That's going to be 4 mu 0 I divided by root 2 pi L. Done. Ta-da! That is the answer. So we have solved our problem. Stay tuned for more. See you next time.